we'll cover something like uh, the family of circles which is there. Actually, shouldn't be family, it's basically a pair, but yeah. So here now we have certain important concepts here. So there'll be more than one circle in these scenarios. So for example, and just for like a generic case, let's take the circles that are distinctly positioned. This like this can be used to derive results for these type of scenarios. They are touching each other and stuff. Please remember from a wording standpoint that if the question says that the circles are tangential, or if the question says that the circles touch each other externally, so those things will mean that the circles touch each other like this. So these are tangential circles or touching externally circles. Right. Similarly, if they say that a line touches, like from P touches the circle externally, which means that the line is a tangent. Because at times they may not directly tell you that that line is a tangent. They may say something like the line from P touches the circle externally, which means that it's a tangent. If it says that the lines intersect the circle at A and B or at 2 points, whatever, then it will obviously be a secant. But touching externally in geometry always means touching at one and only one point. In circular case, it will be a tangent. In circle's case, it will be like this point of intersection. So just to sort of, because at times like getting from the word problem to the diagram itself gets tricky. So that's why. Okay, so this is, we'll note down some things for this case. Like for example, this, and you have this. So two circles here in this case. We'll see cases of more as well when we come to the question, but the results, let's have it with respect to this. So if you have two circles like this, right, there's obviously four tangents possible as we had seen before as well. So two will be this, and these are called direct common tangents. These two tangents are called direct common tangents, which is DCT. Why direct common tangents? Because they are on the same side of both the circles. So for example, this tangent is on the top edge of both the circles. This tangent is at the bottom end of both the circles. There is another two tangents that can be drawn, which is called the transverse common tangent, which is this one. And similarly, this one, something like this. Cool. So these two basically are TCTs or transverse common tangents. Right. So in this type of a setup, there are two direct common tangents, two transverse common tangents, and there cannot be common tangents more than four, as we saw previously as well, right? So you can have only till two. So that's why like we took this case to like take it as a generic example, and then other cases can be derived and are much simpler than this. Now, if this is the center of the bigger circle and this is the center of the smaller circle, of course, these radii will be perpendicular to the tangent. Radius is always perpendicular to the tangent. Okay, so for example, if we draw a radius here, we mark this as r, we mark this as small r. So small radius, bigger radius, etc. Right? And yeah, so this intercenter distance is d, let's say. So this distance between the centers is d. So let me just distance between centers is d. So the length of the direct common tangent for these two, which is basically this length and this length, is nothing but square root over d square minus r1 minus r2 square, on this case r minus r square, the difference of the radius basically. Or for here, if we were to write, it will be d square minus capital R minus small r, the whole square. This is the length of the direct common tangent. Please remember this. The length of the transverse common tangent, which is these two, very similar formula. The only thing is it becomes r1 plus r2 square, which means if for this of the above case, it will be r plus r square. This is the length of the transverse common tangent. Okay, so again, you can see from the equation themselves, right, that these things are same, d square is same, minus is same. The only difference is r minus r and r plus r. So obviously, in the case of direct common tangent, a smaller amount is getting subtracted. Like you're subtracting r minus r from this. Here you're subtracting r plus r, so it's a bigger number getting subtracted. So always DCT will be bigger than the TCT in length. Right. So even if you like get confused between the formulas, like okay, what was DCT and what was TCT, so it will always help to remember that DCT is greater than TCT. And again, from the formulas, it is very, very clear, right? You're subtracting a smaller quantity here. So this is the first part. And again, if you like sort of try to generalize it for other scenarios, for example, here the circles were distinct completely and we derived this, right? So now if the circles are, for example, touching each other tangentially or touching each other externally, as we just mentioned, so what will be the length? And again, in this case also, there will be these tangents, right? So what will be the length of direct tangent here? So here the DCT, what will be the DCT? So here we know that for this case where the circles are touching each other externally, the D is R1 plus R2 as is visible. The distance between the centers would be the sum of the radii. This is D. So just replace D by R1 plus R2 in these formulas and you'll get. So for example, for the direct common tangent length, it will be D square is R1 plus R2 square minus R1 minus R2 square. Right, so okay, if you want to do this, then it will be like 4 R1 R2 or
Hello?
2 R1 R2. Yeah, because you can infinitely extend this tangent, right? So it will always be from one circle to other, the line segment between those two circles. And for the transverse, it will be this line segment here. So that is the length. So for example, if you saw here, right, that for this particular case, we just replace small d by R1 plus R2 and we got the expression for this. Obviously, R1 square, R2 square get cancelled here and 2 R1, R2 gets added and you get 4 R1, R2 or 2 root R1, R2, right, or 2 root uh, small r, capital R, based on whatever you name, right? So hopefully this is clear. So the major, basically the thing to remember here would be this. So this is the first part of what we need to know about families of circles, right? And since this is a direct formula, so like it is like sort of easier to pick up. You won't have to like figure it out much because the moment you see that they're asking that, so you can cure that. Just let me just remove. Okay, the next thing with respect to the same setup, basically, right? And this is the part which will be more like geometrically useful, which is not a direct formula. Here, it's a similar setup, just like reverse the circle orders and stuff. So again, this is capital R, this is small r. This is, let's say, P, this is C1, this is C2, and the intercenter distance is once again D. But all those things are not like sort of very useful here because like this, the property that we're going to discuss right now is more of a theorem than a formula itself. So what this says is if you join the center of these circles, like okay, let me just for example, if you join the center of these circles to this point P. So the first part of the theorem says that C1, C2 and P will always lie in the same straight line, right? And this may sound pretty like easily intuitive, but yeah, just good to note because people might have questions that okay, how do you know that it will be in the same line? But it will always be in the same line. It will be in the same line, right? And again, we can draw the radius here as well. This is capital R, this is small r, etc., right? But the most important thing and the most major takeaway from this is that all of these triangles will be similar. Like this small triangle will be similar to this big triangle. So if we were to just name the points right here. So triangle PNC2 will be similar to triangle PNC1. Why will they be similar? Because this is radius tangent 90, this is radius tangent 90. So 90 means that same line, two perpendicular, so this will be parallel, which means we have covered this as well, that this will be similar. And this angle is common between the two triangles. Similarly, triangle, let's say if we name this Q and R, okay, no R is there, but let's say Q and T. So triangle P, C2 and Q, this triangle will be similar to triangle P, C1 and P, which is this triangle. Why? Because again, this and this lines will be parallel. Here, these two lines are parallel. Very, very important result because would be used in questions quite often. Like when basically, if any question you see that there is such kind of a setup, right, and there can be like 2 or 3 circles, but similarity will always end up getting used in such questions. Because what is the implication of these things? This being similar, okay, now we understand that okay, triangles will be similar, but what is the implication of this? The implication of this would be that all of these sides will be in the same ratio. So for example, if we take this triangle and like the PN C2 and this triangle which we just said were going to be similar. So essentially what that means is PM by PN will be equal to PC2 by PC1 will be equal to small r by capital R. Right. So this small length by whole length will be equal to this small length by whole length, and both of them will be in the same ratio as the radii. Right. So this will end up getting used at quite a few places actually. And it should like if in an exam a similar diagram comes, similarity should be the first thing to strike your mind. And we'll cover some questions on this as well. So no need to worry. Like in terms of examples, we will cover questions. But yeah, these lengths are, and this will always hold true. Even if you have like three circles here. For example, you have this, this, right? So if you take like two at a time, that similarity will also work. For example, if you take these two, so this triangle, let me again name this ABC, will be similar to PQC. Again, because of the radius tangent 90 degrees setup. So in these two triangles, again, basically AC by CP will be equal to CB by CQ will be equal to, this is R1, let's say, this is R2, so R1 by R2. Same thing you can do for these two triangles, the circles as well, and you should be good to go. So this will always hold true. So this is the second aspect of it in terms of this. So like if you are given some of the lengths, right? So one case could be that okay, you are given some of the lengths and you are asked some of the lengths. So in that case, similarity comes to direct use. You can use these relations, and in case like you're given sides and you're given some angles as well here, you can use basic trigonometry because again these angles will always be 90. The radius tangent thing. Cool. Any questions on this? Awesome. Now there are a couple of things basically that we just need to touch upon, and after that we can just directly move to questions. So obviously radius perpendicular to tangent, you know that the angle between tangent and radius will always be 90. Similarly, another application which comes is basically from the, if you have a chord here, this is the center, you drop a perpendicular from the center to a chord, it will always bisect the chord. Like it will always hit at the midpoint of this chord. So AM will be equal to MB whenever this is a chord and the perpendicular is being drawn from the center. Okay. So and the reverse is also true. So for example, if somebody tells you that a line is drawn such that it bisects the chord, so that should tell you that it's a perpendicular line only. And it's a very easy derivation because these two triangles will be congruent. This is same because both are radius, right? Then this is common, and let's say if they give you that it's a perpendicular, so by RHS congruency these two triangles will be congruent, which means this and this will also be equal. So midpoint, right? A second related theorem to this is basically equal chords are equidistant from the center, which is also intuitive because let's say you have this chord here and this chord here and these both are equal. So if you just see basic Pythagoras, right? So this perpendicular will bisect this perpendicular will bisect this. So if you see Pythagoras, then this will be R, and then this length, you can derive this basically, and if they are equidistant, so this will be equal to this, which means this will also come out to be equal, like x will be equal to, if this is x, this will also be xy, because these were equidistant. And in geometry or in mathematics in general, whenever the word is only distance, then it generally means perpendicular distance, because perpendicular is the shortest distance. And this is like not only relevant to circles, but for the whole of geometry. If somebody tells you that okay, like let's say this is a line, right, and like there is this point here. So what is like the shortest distance from this point to the line, because there will be many distances, right? The shortest distance will always be perpendicular distance. So anyways, so yeah, so basically this is how it sort of gets derived, that equal chords are equidistant from the center. Reverse is also true. If the chords are equidistant from the center, which means the chords will be equal, right? And if we combine it with something that we've just learned a few minutes back, that equal chords subtend equal angles, so essentially all these three things are equal. If the chords are at equal distance, then the chords will be equal and they'll subtend equal angle at center. Okay, so that sort of covers uh, like most of what we need to know. And again, as we do keep doing questions, if something is specific for a special case or something, then we'll cover it there as well, because there are quite a lot of questions to cover. But any doubt anywhere on the conceptual part of this or the theory of this, basically? There's one other part that should be mentioned, which is a cyclic quadrilateral. And let me just start that on a new page. Right, so quadrilateral inside a circle, as you would know, is a cyclic quadrilateral. So in this case, ABCD is a cyclic quadrilateral with sides, let's say PQRS. Area of a cyclic quadrilateral would be S minus P, S minus Q, S minus R, S minus S. A very simple version of the Heron's formula. The only thing is, okay, since we've already used the alphabet S, we should use something else there, S minus Y, let's say. So just like from each side, take the difference of the semi-perimeter and you're done. S is nothing but P plus Q plus R plus Y by 2. The general semi-perimeter that we know, right? So half of the sum of lengths, and the area is S minus P, S minus Q, S minus R, S minus Y. And a couple of things to know about this area, right? So first of all, like similar to Heron's, but the outside S is not there. In Heron's, we used to have root over S into S minus A, S minus B, and so on. So this S used to be there, which is not there in this formula. Okay, so this is the area of the cyclic quadrilateral. This people know. What a lot of people would not realize is that a cyclic quadrilateral has the largest area among all quadrilaterals if sides are given. For example, if you're asked that, okay, there's a quadrilateral, you're not told what quadrilateral it is. If there's a quadrilateral with sides like 11, 12, 13, 14, find the area of the largest quadrilateral that can be made with these sides. The largest quadrilateral will always be a cyclic quadrilateral. So you'll calculate S from here and you'll just subtract S from the sides and multiply them, take a root over, and you're done. So this is a property of a cyclic quadrilateral, that if the lengths of the sides are given, then you need to sort of apply this formula for a cyclic quadrilateral to find the largest quadrilateral with those sides. Right, now there's one very popular property of cyclic quadrilaterals. Like one is obviously a more basic property, that opposite angles are supplementary. So theta and 180 minus theta, if this is, let's say, x, then this will be 180 minus x. Opposite angles are supplementary or add up to 180. Right, so this again is something, yeah, pretty basic. But the other property that is again exclusive to cyclic quadrilaterals is something called the Ptolemy's theorem. Here again there is something that most people would know, and something that might have gotten missed. The Ptolemy's theorem basically is for a cyclic quadrilateral and it relates to the diagonals. Again, it may look like a rhombus or something, but it's not, it's just general quadrilateral. Right, so basically Ptolemy's theorem says that the product of the diagonals AC into BD will be equal to the sum product of opposite sides. So it will be AB into CD. This is product multiplication. Will be AB into CD plus AD into BC. Product of the diagonals is AB into CD plus AD into BC. So you take the product of opposite side, you add them up, and you get the product of the diagonals. This is Ptolemy's theorem. This is the part that people would typically know. Coming to the next part of this, if let's say I give you the sides of the cyclic quadrilateral, for example, like 10, 11, 12, 13, anything basically, right? And you're asked to find the diagonals. How to find them? Like individually, not the product. Right. So if you're given the sides, you know the product can be easily found by 10 into 13 plus 11 into 12. You're done. But if you're asked the diagonals themselves, how to do it? So clearly, one thing is evident that if I know only this, I'll be able to find the product of the diagonals, but I need one more equation because there are two variables. So I need one more equation there. And this is why you should keep in mind the formula for the ratio of diagonals as well, which is AC upon BD. It's also a simple formula. Just follow like what I'm about to say. Just see each letter. So you start with A. You start with A. Then see the sides that join up to A. So it will be this side and this side. So AD and AB. So just multiply them. AD into AB. See the second letter C. See the sides that join up to that. So CD and BC join up to C. So this will be plus and CD into CB or BC. Over. So A and C are done. A was being formed by AD and AB, you multiply them. AD into AB. C was being formed by CD and BC, you multiply them. CD into BC. Same thing for denominator. What is B made up of? AB and BC. So AB into BC plus what is D made up of? This and this. So AD into CD. And that's it. This is the formula for the ratio of diagonals in a cyclic quadrilateral. So now you have if I give you the sides, you're asked the product. That's a direct formula. But if you're other diagonals, then you need one more equation. So you'll find out the product of the diagonals. You'll find out the ratio of the diagonals. Solve those two equations and get the diagonals themselves. Cool. And again, depending on like what their additional data that they've given in the cyclic, for example, if they give you like, okay, like AB was a diameter, then obviously one of the angles subtended like by that chord will be 90 and all of that. So that can be like that's an additional detail and all if they give you some additional detail to figure these out. But if they only give you the sides, then this is the method to figure out the diagonals. Okay, and once again, if the side lengths are given, then the largest quadrilateral that can be made from those sides is not a parallelogram, is not a whatever quadrilateral, it's just a cyclic quadrilateral. Cool. So with that, we come to the end of the circles concepts and theory. So now we'll start with the questions. Cool. So let's start with this. And again, please, like in some questions, I'll keep mentioning that this is a standard type of a setup. So like sort of keep those in mind so that if you see a similar setup in exams, like for example, this question, the setup that we're going to use for this question is a very standard sort of a diagram that you'll see in several places, right? So if you just identify the diagram, it is easy for you to come up with the approach. Again, not to memorize, but just to sort of relate that, okay, I've done something like this before. That's the only like output. Okay, so tangents OA, OB from the point O are drawn to a circle with center P. You're given, okay, let's just first start with the diagram. Center is P, OA and OB are the two tangents that are drawn. OB is 204. Of course, OA will also be 204 then. And AB is 192. So AB is the chord that is being formed because of the points of tangency. So this is 192 and you're asked to find the radius to the nearest integer and the options are given. There is a center, this is the chord, these are the two tangents, we know the lengths of these. Very typical setup, and the approach that we're going to discuss is going to be as in useful to apply at similar setups ahead as well. So first things first, right? So how to strike this first of all, right? Now we need to find the radius to nearest integer. So first of all, we should make the radius itself, right? Now in this setup, and again, it's important to know the thought process of coming up to the method, right? So that you know how to hit the question basically. You know that you have to find the radius, you know a chord. Whenever you have to find the radius, you know a chord. One of the most direct ways to basically drop a perpendicular here because we know that it will intersect at the midpoint of the chord. So basically, if I was to do this here, it will split the chord into like 96 and 96, sort of that, right? And I know this chord length, but if I do only that, the problem with that is I need to know one more side, right? Like let's just draw the perpendicular here, right? So here, if this is a perpendicular, I could have found out the radius from doing only this if I knew this length. Because in this triangle, I would have directly applied Pythagoras and found it out. But that is not possible here because I don't know this length. So I need to figure out this length first. I know this is going to be 96 and 96. What else do I know? And again, in such questions, right, it's always good to, like, whatever you can know or whatever you can derive from the question, to just make a note of that in the diagram, so that all that can be fetched from the question is fetched. And that is very important because the difference in, like, two people knowing the same concepts might just differ in, like, what they could collect from the question, and else and hence it can be the difference. This is also 90 because again radius tangent. So what do I know now? 90, 90, the length I know. Find the radius to the nearest integer. I drop a perpendicular because that is what I'll do if I'm given a chord and asked to find the radius. Okay, now I know that this, let's call this point M. I need to find out this length. Once I get this length, I'm done. Right. Now, what is this length? Basically, let's call this X for now. Like MP basically is equal to X. There seems to be no direct way to get to this length, right? So let's try getting this length through OP minus this. If we can find OP, we can find X. Why? Because this length we know. MO we know. Why do we know that? Because it's a Pythagoras theorem. This is 96, this is 90 degree because we dropped the perpendicular, and this is 204. So again, this is again part of the data that you should just directly collect from the figure and just mark it on the figure that, okay, this I know. So OM will be equal to root over 204 square minus 96 square. Okay, so this is basically root over 204 plus 96, which is 300, into 204 minus 96, which is 108. So this will be 108 into 3 is 324, 324 is 18 square, so this will be 180. So OM we know is 180. Done. Right, so if I can find out OP and I subtract 180 from that, I should be able to get this, right? So in this triangle, basically, if you see AMO, we know all the three sides now. This is 204, this is 96, this is 180. We know all three sides. So let's use our knowledge of these three sides to derive other sides. And what is the most important, the most commonly used principle whenever you have such a situation? That is similarity of triangles. And why similar triangles struck me? Because it immediately struck me that if this is 90, which means this triangle is a right triangle, also this is 90, so this triangle is a right triangle. Also, both of the triangles have a common angle of this one. So this small right triangle and this big right triangle should be similar, common angle of 90. If I know the sides of one of the triangles completely, I should definitely be able to figure out the sides of the other triangle. So that is how you're supposed to, like, strike that, okay, immediately two angles seem the same. So similarity should be helpful to me. So triangle AMO, which is the smaller triangle, and it again, it's important to name these triangles carefully in terms of similarity. The first you can name in any order. The second, while naming the bigger one. So we know that O will be the same as O because it's a common angle. M was 90 in the smaller circle. So in the big circle, you have to search for the 90. Show that it's equivalent. So in the big circle, what is 90? A is 90. A, and the remaining becomes this one. So AMO is similar to PAO. Right. Now I need to have a relation in R because that is what the question is asking. Maybe, right? So what is R? R is nothing but PA. So let's write equations for PA. So basically it will be AM over PA is equal to AO by PO equal to MO by AO. These three equations will be there. What is AM? AM I know is 96. Why again 96? Because 96 was half of 192, perpendicular from center to chord, bisects chord. PA is the radius which I need to figure out. AO is 204. PO, I don't know. Okay. MO is just figured out, 180. AO is 204. Cool. So now I have these relations wherein basically, yeah, exactly. So any doubts till this point, like how we derived similarity by the 90-90-90 equivalence and how we wrote the side ratios? And again, just to name it once again, AMO was the smaller triangle, and the bigger triangle would be PAO because O is common, and M in this would be corresponding to A in this. And yeah, this is the radius. So this can be used to find the radius, and you're done. So okay, fine. So this will give R as basically nothing but 96 into 204 by 180. So okay, let's just cancel what we can. So 204 and 180 can be cancelled by 12, it would seem. So 1 and 17. 1596 is 5 and 32. So 32 into 17 by 5. So 17 into 32 would be 17 into 34. So 544 by 5, which is 108.8. So nearest integer would be 109. This is the correct option there. Right. So always remember in such setups wherein you have like, a chord getting formed here and from an outside the tangents are getting drawn and that sort of gives this. So similarity would be pretty helpful in those scenarios. Cool. So